Hi and welcome to John's Maths book. In this video, we're going to be looking at finding the area of a sector of a circle and its arc length. If you like the video, then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. Let's focus on the sector of a circle and how to find its area and associated arc length. A circular sector is a portion of a circle or disc which is enclosed by two radii and an arc. In the diagram, it's the blue shaded region. If the sector angle, so theta in the diagram, is less than 180 degrees, then it's known as the minor sector. If it's greater than 180 degrees, then it's the major sector. I'm going to look at different techniques for finding the sector area and its associated arc length. Each technique will depend on the information provided. Let's now rotate around the angles of a circle in a counterclockwise direction and see what angles we pass through. When we reach a quarter of a circle, we pass through 90 degrees or pi divided by 2 radians. And at half a circle, we've passed through 180 degrees or pi radians. And at 3/4 of a circle, we've advanced 270 degrees or 3 pi divided by 2 radians. And when we complete the circle, we've travelled through 360 degrees or 2 pi radians. Now we understand that a sector of a circle is a portion or fraction of its total area. Let's find the area of a sector given the radius and sector angle in degrees. So this circle has a radius of 4 and a minor sector shaded in green with an angle of 60 degrees. The portion or fraction of the circle taken up by this sector is the sector angle in degrees, in our case 60, divided by 360. Where did we get the value of 360 from? Well, as we saw earlier, it's the angle that makes up a complete circle. So the fraction 60 divided by 360 simplifies to 1 divided by 6. Now, given that we know that the area of a circle is pi times the radius squared, the sector area is a fraction of the total area. So our fraction is 1/6. So we need to multiply the total area of pi r squared by 1/6. When we do this, we get the area of the sector. So in our case, the area of the sector is pi times the radius squared. So the radius is 4. So 4 multiplied by 4 and then multiplied by our fraction of 1/6. So if we do multiply that out, we get 16 times pi divided by 6. If we divide the numerator and the denominator by 2, we simplify this fraction and we get 8 times pi divided by 3, which gives us the area of our sector. Now let's see what happens when the angle theta subtended is given in radians. In the example here, we have a subtended angle theta of pi by 3 radians. This is equivalent to 60 degrees. As a quick recap, to convert between radians and degrees, we multiply the angle in radians, so in our case pi divided by 3, by 180 divided by pi. And as you can see, this gives us 60 degrees. If we're going the other way, from degrees to radians, we take the angle, so 60 degrees, and we multiply it by pi divided by 180. This gives us pi divided by 3. Let's now calculate the portion or fraction of the circle covered by the sector shown in green. As before, it's the subtended angle theta divided by the angle that makes up a circle, which in radians is 2 pi. Therefore, we have theta, which is pi by 3, divided by 2 pi, which equates to 1/6. So now if we take our fraction, which is 1/6, and multiply it by the area of our circle, which is pi r squared, we get pi multiplied by the radius squared. So that's pi multiplied by 4, and then multiplied by our fraction of 1/6. That will give us 16 pi divided by 6, and dividing numerator and denominator by 2, we simplify it to give us 8 pi divided by 3. So this gives us the area of our sector when the angle theta subtended is pi divided by 3. We should note here that when working in radians, our area is given by pi times r squared multiplied by theta in radians divided by 2 pi. The pi in the denominator cancels with the pi in the numerator. This leaves us with an equation of 1/2 times r squared times theta in radians. So for our example, we have 1/2 multiplied by the radius squared, so that's times 4 multiplied by pi by 3, which is the angle in radians. So this gives 8 pi divided by 3 as our sector area. Now let's look at the arc length of a sector of a circle. The arc length is a portion or fraction of the circumference of a circle. So if we know the subtended angle theta and radius, we can calculate the arc length shown here. Let's first see how we do it when the sector angle is in degrees. If we have a subtended angle theta of 60 degrees, then the arc length is a fraction of the total circumference of the circle. The fraction or portion is given by the subtended angle, so in our case 60, divided by 360, where 360 is the angle that makes up a complete circle. So our fraction or portion is 1/6. The circumference of a circle is given by 2 pi r. So the arc length of a sector is given by the circumference, 2 pi r, multiplied by the fraction. So in our case, 1/6. So the radius in our case is 4. So we have 2 pi multiplied by 4 multiplied by 1/6. So the arc length of our sector is 4 pi divided by 3. Now let's look at finding the arc length of a sector when we're given the radius and angle in radians. So in our example here, we're given an angle theta of pi divided by 3. The portion or fraction of the circle represented by the sector is pi divided by 3 divided by 2 pi, where 2 pi is the angle that represents the complete circle. The fraction, therefore, in this case is 1/6. So our arc length in this case is given by the circumference of a circle, which is 2 pi r, multiplied by the subtended angle theta, which in our case is pi divided by 3, divided by 2 pi. So we can see the 2 pi in the denominator cancels with the 2 pi in the numerator. So our arc length, denoted by s, is equal to the radius multiplied by the subtended angle theta. So s is equal to the subtended angle theta, so pi divided by 3, multiplied by the radius of 4. So the arc length s is 4 pi divided by 3. We should note here that we can only use this formula s equals r theta when we're working in radians.